So one more thing about this model here I want to say before I move on with that. This model is also used for modeling atomic transition absorption. Atomic transition absorption is actually a quantum mechanical effect, but you can use a semi-classical picture to model it. Because if you think of this, an absorption happens, then there will be some kind of a spectroscopic line shape. If you look at the epsilon, you might have something like this. And this attenuation gives this absorption line a finite cube. Okay, and this is when you hit the resonance of the atom. When you hit the resonance of the atom, and the atom might transition from a lower energy state to maybe a higher energy state, which you still can model with the spring when you can transition with the spring. And when you hit this resonance, which can be governed by Fermi's golden rule, okay, you will have this sharp line. And this is kind of a semi-classical picture of that. And they also use that to model this kind of atomic transition, use absorption. And instead of just using one frequency, you can use a multitude of frequencies, because there could be many, many atomic transitions in the molecule. And then you can actually use fitting model to fit any kinds of epsilon to this kind of model. You can add in maybe something like this over here. And in different kinds of molecules, different kinds of laws, different kinds of something. You can fit almost anything to this model. Okay, that's a semi-classical model. And this actually has been fitted, the Summerfield group model has been fitted to experimental data. And they seem to work quite well at long wavelength, and optical wavelength, when the optical wavelength is much larger than the size of the atom. As the optical wavelengths get shorter and shorter, then you start to excite atomic transitions. The Summerfield group model doesn't work very well, and you have to resort to some other curve fitting model and maybe more quantum mechanics model to model the epsilon correctly. So let's talk about surface plasmons. Surface plasmon. And it usually has a very long name, I don't know why. Okay, polaricon. Surface plasmon polaricon, which I think is a fairly classical phenomenon. Okay, and this phenomenon happens at the dielectric interface, a gold-air interface, for instance, or silver-air interface. That happens in the real world. Okay, and as I said before, this effect is very similar to the Brewster angular effect. Instead of looking at the numerator for the reflection coefficient, you look for the pole in the denominator. So Novotny and Heck went through some detailed derivations, but we don't have to do that. We just have to look at the reflection coefficient and look at the numerator and the denominator. So we can actually get the physics of this just by looking at this reflection coefficient. In the book, in the textbook that Novotny and Heck wrote, they study an interface problem where they have epsilon 2, mu 2 over here, epsilon 1, mu 1, and then they have z-axis here, and I guess they have an x-axis over here, and then they send in the light at this angle, theta 1, theta 2. And then they start to match boundary conditions and obtain the formula for the surface plasmon polaricon. But we can do that very easily using a different approach, which is that you can look at R12 Tm, which is given by epsilon 2 K1z and epsilon K2z over epsilon 2 K1z plus epsilon 1 K2z. we know this reflection coefficient. And we know the physical meaning of what a pole means. A pole means that a solution exists without an incident wave. So if the reflection coefficient goes to infinity, it says that you don't have to send in an incident wave. A solution exists, a reflector wave exists. That's what it means. Which means that a natural solution exists at this interface without any excitation. That means that there is a guided move. There's a meaning of a guided move. There's a meaning of a resonance. The resonance solution is a solution that exists without any excitation. Okay? So we can actually look for this. Look for when this pole exists, the pole exists in this regime, and K1z, Kiz is square root of Ki squared minus Kx squared. In this visual picture over here. And then I can square this to get K1 squared minus Kx squared to the epsilon 1 squared K2 squared minus Kx squared. Okay? And then I can solve for my Kx quite easily. I will have Kx squared epsilon 1 squared minus epsilon 2 squared. This is to the epsilon 1 squared K2 squared minus epsilon 2 K1 squared. And then Kx squared hence should be equal to, let's assume that mu1 equals mu2. That is usually what happens at optical frequency. It's very hard to get magnetic material at optical frequency. Okay, there are some physical reasons for that, but it's very hard to do that. But it's very easy to get polarizable material at optical frequencies. Let's assume this to be true. I don't really know. I can say something, but it probably is not correct. Okay, I don't really know the true reason. It's probably very hard to get magnetic dipoles at optical frequencies. And there are people who work on that and trying to find ways to make magnetic materials at optical frequencies. Like this guy, what is his name? I think his name is Kevin Webb at Purdue. He's studying this kind of problem. Okay. And I forgot one more thing. Another thing that you should know is OCT, optical coherence tomography. This is Steve O'Hart specialty. Okay. Optical coherence tomography is also a new optical technology, very important. And it actually is used for detecting surfaces, cancers in surfaces. It's a very popular technology. It works the same way as ground penetrating radar. You send in a pulse, optical pulse, and you look for reflected pulse, and then trying to use interferometric effect to figure out the amplitude of the reflected signal. And from that, you can actually deduce what the layering should be in the human tissue on the human surface. Again, this is another example of microwave engineering being translated to optical frequencies and becoming very useful. Okay, I'm not saying that those works are not difficult. They're very difficult work. Having to do them on optical frequencies is very difficult. But a lot of our knowledge that we know in classical electromagnetics can be translated 1,000 times or 2,000 times or 10,000 times up in frequencies, and then it becomes very useful technology because it's never been done before. Okay, so this is another example of ground penetrating radar physics being translated up into optical frequencies and becoming very useful. Okay, so there might be a lot more of those things. You can just have to look around. If you think that classical electromagnetics is not finding new technologies in the microwave area, just go up in frequencies. There are probably many new technologies waiting to be discovered by you. Okay. So this is another thing. Yeah. So if I write this out explicitly, so this omega squared mu epsilon 2 epsilon 1 squared minus omega squared mu epsilon 1 epsilon 2. Did I get it right? No. There's no square. Yeah, there's no square there. Divided by epsilon 1 minus epsilon 2, epsilon 1 plus epsilon 2. And then I can take out something common. Did I do this right? So there's a square here, right? Epsilon 1 squared minus epsilon 2 squared. There's a square there, sorry. Square here, right? So this is right now, I think. Okay, so I can pull out a common factor. And then I will have epsilon 1 minus epsilon 2 in the numerator, epsilon 1 minus epsilon 2, epsilon 1 plus epsilon 2. And then these cancel each other. I have the Brewster angle formula. So the surface plasmon formula for the surface plasmon polariton, which is usually short named SPP. You see this name quite a bit. Okay, SPP. Okay, that formula gives you the fact that Kx is equal to plus or minus K, where K is omega. Let me see what I have. Okay. I can call this relative permittivity, and then I can define my K. We just that, and this would be relative permittivity. I think that's what the textbook uses. Okay, call those relative permittivity. Okay, so then this is a rather confusing thing because we square things and then we derive this formula. If you were to look for the Brewster angle, you would have done the same thing too. You would have written this equation down. You have written that equation squared, you get exactly the same formula. So that formula there is good for Brewster angle as well as the SPP, surface plasmon polariton. So how do we decide what sign to choose in the square root? Because both physics give rise to the same formula. You pick the sign so that this actually becomes 0. Okay. So say if say this is metal, okay, this is gold or silver, okay, metal. You know AU means gold, AG means silver, right? So when I was in Hong Kong, the students don't like to use gold and silver. They always say AU, AG. I wonder what they meant. Say AU, AG. I finally figured out that they meant gold and silver. Okay. So if you have gold on silver, then what happens is that you will have to pick. So one of this can be negative. Okay, you have to pick the sign so that this goes to 0, and you pick the kx in such a manner that that denominator cancel each other. Okay, that denominator cancels each other. And you do things accordingly. So if I work out, say, kjz squared will be equal to kj squared minus kx squared. And that would give me something like kj squared minus epsilon 1, epsilon 2, over epsilon 1 plus epsilon 2, k squared. K squared is just omega squared u epsilon. And then so this could, like, if this is k1z squared, this would be omega squared mu epsilon 1, or it could be k squared epsilon 1. Okay, this would be k squared epsilon 1. And then the second term would be epsilon 1, epsilon 2, epsilon 1 plus epsilon 2. And this would give me k squared epsilon 1 squared plus epsilon 1 plus epsilon 2. Okay, I think that's correct. These are relative permittivity. So if you have k2z squared would be k squared, and if this is epsilon 2, still cancel each other. So it's epsilon 2 squared over epsilon 1 plus epsilon 2. Okay, so k1z squared and k2z squared will be given by those values. And they will have to be negative in order to have an evanescence wave in each region. Okay, so one way for it to be negative is that the numerator becomes negative and the denominator becomes negative, or just the denominator becomes negative and the numerator becomes positive. So one way for, and then kx has to be real. Kx approximately real. So if this is a surface mode that propagates along like this, okay, kx has to be real and kz has to be imaginary. So you can see that in order for that to happen, the thing inside, the square root sign here cannot be negative. So one way for this thing not to be negative is that epsilon 1, epsilon 2 is positive or negative. Because one of this is negative, okay? And then you have epsilon 1 plus epsilon 2 is negative. If you have both of these been satisfied, then this kx can be real and positive, and you can have a propagating mode. You can have an SPP guided on the surface if this fact is true. And this fact does happen for the Go particles, Go metal, and silver matter, because epsilon 2, but epsilon 1 is negative in this picture over. Epsilon 1 is negative. Well, of course, this is the lossless case. In the ideal case will not, the real world case will not be lossless. Epsilon 1 and epsilon 2. Epsilon 2 can be air, so it can be real, but epsilon 1 usually has a more imaginary part. Okay, so kx will not be purely real. It will have some attenuation. That is the difficulty that we face. That this surface plasmon polaricon decays as it is guided by the surface. If it does not decay, when it's been guided by the surface, it will have lots of applications. But unfortunately, that is not the case. It decays because of the fact that if you look at a group sum-of-field model, this cannot be purely negative. Okay. So if this is negatively squared, it will be positive, but the denominator will be negative by one of these rules. If this is negative, then K2Z is pure imaginary, and you will have cap modes. And if this is true, then the denominator is negative, and K1Z will also be evanescent wave. Okay, so this gives rise to real Kx and then imaginary K1Z and K2Z. This implies the presence of 3p. So, there's another thing that you notice, which is that if the denominator goes to 0, which could happen if epsilon 1 plus epsilon 2 tends to 0, then kx tends to infinity. Kx tends to infinity. When kx tends to infinity, what happens to kgz, kjz? It becomes highly evanescent. So when the thing becomes highly evanescent, the mode is very well trapped, highly confined. Very highly confined. Decays exponentially in this direction. It also decays exponentially in that direction, and we have a highly confined mode. And that actually gets a lot of people excited, because you can get the mode to be much more better confined than an optical fiber. In an optical fiber, you have a guided mode. You have a guided mode. You can make the core very, very thin, but the mode is actually not confined. The mode is actually somewhat like that. And because of that, you have to bundle optical fibers with a certain distance apart so that they don't talk to each other. There's no crosstalk between the optical fibers. You have to have a cladding around the optical fiber. Put some cladding here. Because this mode is not confined. And another field that has been developed in the past that was causing a lot of excitement but didn't take people very far was the area of optical integrated circuits. Okay, optical IC. So at the time, people were hoping that you can make waveguides at optical frequencies using dielectrics. Rich waveguides to make things like this, and then you start to confine optical signals, or you might make things like this by doping, and you make all kinds of waveguides like this with optical integration techniques. But then the problem with this kind of waveguide is that the mode is not highly confined. You can show that the confinement distance is on the order of wavelength. This thing is on the order of optical wavelength. You can also show that if the mode is guided in this, the confinement is on the order of optical wavelength. I think I told you how to prove this before. Okay. So optical wavelength is quite long. Infrared is about maybe 1,000 nanometers. Blue is about 400 nanometers. But what about electronic IC? We can make wires on the order of 10 nanometers, 20 nanometers now. So for that reason, optical integrated circuit never could compete with electronic integrated circuits. Because in electronic integrated circuits, we can make them very, very small. We can pack a lot of transistors and ICs within a very high density. And the electrons are confined within those wires, even though they leak out some electromagnetic fields. If you do your electrical engineering correctly, you can make them very small. You satisfy Kirchhoff current law, Kirchhoff voltage law. You can design electronic circuits that are very small. But you cannot design optically integrated circuits that are very small. There's no Kirchhoff current law, Kirchhoff voltage law for them. The only law is the law of waveguides. And it couldn't make those waveguides any smaller. So that field actually created a lot of excitement for a while, but did not deliver as does electronic circuits, as does the IC industry. Okay, but when this came about, there's a lot of excitement about it. Surface plasma polariton, you can confine the field, but the only obstacle now that we face is the loss. Okay, the loss is high because of this problem. Okay, the loss is high. So let's look at some of the salient features of this surface quantum polarity function, how it looks like. And if you were to plot the omega k diagram, omega kx diagram, it should look something like that. There's a omega kx diagram of the what we call the light one. If there's no guidance, there's no waveguide, omega k diagram will follow that of free space. Essentially, it becomes omega k, omega over c is equal to k. Omega is equal to kc. So omega k diagram will look like a straight line. If there's no confinement, there's no guidance, okay? But now if you were to want to have confinement inside a certain region, then the wave has to be slower than its environment. The light line is that of free space. So in order to have something guided, if this is free space up there. In order for this to be evanescent up there, okay, kx has to be larger than k naught, that of free space. And kx is larger than k naught means omega over kx is smaller than omega over k naught. What is omega over kx? The phase velocity, right? So the phase velocity of the waveguide has to be slower than that of the phase velocity of the free space. So if k naught is larger over here, so this line must have a slower slope. Am I right? The velocity of that line will be slower. Because the slope of the line is c, right? So if the slope is lower, the smaller the velocity. So in order for you to have confinement, you have to design a slow wave structure. For those of you who do leaky wave antenna, you would know that you have to design slow wave structure so that the wave is confined to the surface, confined to your structure. So we want to slow down the wave, and it does happen. So if you put in dielectric material, it slows down the wave. That happens with dielectric waveguides as well. But there's something unusual with this waveguide, which is that if you hit the resonance frequency, so the epsilon 2 becomes very negative. Epsilon 2, just using a very simple plasma model, epsilon 2 is just equal to this thing. So if you hit the plasma resonance frequency, epsilon 2 can become very negative. Okay? And then this curve just veer off like that. Kx becomes infinity. There's confinement. And what happens is that Kx just goes to infinity because this thing goes to 0. Okay, so the line just veer off like that. And Kx remains real. We want this to remain real. Numerator is negative, denominator is negative, but this has a very small negative part because this almost cancels each other. So the curve will look something like that. This is the dispersion diagram on the SPP. This is how it looks like. Okay.
Why is epsilon 2 very close to epsilon?
What is that?
You said that denominator goes to 0.
Denominator goes to 0 because epsilon 2 is a plasmonic material, so it can become negative. And if it happens that as you change frequency, it's negative. Okay, it's negative when the frequency is low. But as you raise the frequency, its value is going to change. It will hit a certain frequency where these two are almost equal to each other. And when you hit that frequency, then Kx becomes infinity. Kx becomes infinity. And you can actually solve for the frequency using this simple closed plasma model. very easily. Okay, we just want this, say for the cold plasma, we assume that everything in the background is equal to this, right? We want this to be -1. And then if you solve for the frequencies, then the frequency should be 2 is equal to omega p squared over omega squared. And then the frequency that happens is omega p over √2. Right? Did I solve it right? So when you hit this frequency, when you hit that frequency, this epsilon 2 will cancel this epsilon 1, assuming the epsilon 1 is air. So these are all relative permittivity. Okay, we have already factored that out. And that frequency, this will be omega p over √2. Okay? With this simple model, you can have more complicated root model. You will get a different frequency at which this would veer off to infinity, but this is roughly what happens. Okay. And then sometimes you see this being drawn in many. This actually is the Brewster angle line. That does not correspond to a confined mode, because if you have omega k that looks like that, it actually is faster than free space velocity. And anything with that kind of phase velocity cannot confine. That line is actually the Brewster angle line.
Even for some metals, for example, gold, that's not frequency. It's in the ultraviolet range. And then omega equals to omega equals to omega p over square root of 2.
Right.
It will fall into somewhere near the ultraviolet and make it very difficult.
Right. 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 This is based on a very simple cold plasma. Okay, you can work out more complicated formulas where that horizontal line is, and you will get a different. Actually, I might have those formulas in my notes. Okay, you can work out those formulas. I have done some more. Maybe I didn't have them, but it's in the book. You look at my book. You worked out this formula where this horizontal line is for different kinds of materials. Okay. I don't have it, and I don't have Novotny's book with me either. Okay, but I can give you some numbers. It seems that the 1 over E range is about 60 nanometers in gold, 10 nanometers in silver. Okay, so this is what I gathered from some book. And K1Z is 23 nanometers air. So this is the air part. Okay. And then K2Z is 421 nanometers in gold. Okay, you have gold interface, gold air interface. Those are some of the numbers I get from Novotny's book. I hope I didn't have this reversed. Okay. K1Z is about 28 nanometers in air, and then 528 nanometers in. I hope I didn't have these two reversed. Okay, so these are some of the numbers that are on the order of nanometer dimensions. And if you put in the gamma that we have, some of the formulas where this happens will be quite different. Apparently, that if you put in the gammas that we have, you will have in the denominator something like this. This is the real part of the permittivity. And then you want this to be equal to alpha. And then if you solve for your resonance frequency, this is the real part. There's an imaginary part that I've thrown out. Okay, this is the real part. You solve for the place where the horizontal line should be, it should be given by this formula. Minus alpha minus gamma squared. So this line can be shifted up and down depending on your model. Okay, depending on your model, you can actually shift the line up and down. And it's given in the Walkman's book. Okay, so this is surface plasma polariton. Could be very exciting, and what is more exciting is the fact that you can also make this out of wire. So gold wire or silver wire. And then if you look at the mode of the surface plasma polariton guided on this wire, unlike optical fiber, where you have the mode profile that looks like this, and this is on the order of lambda. Okay, you'll find that the mode guidance is actually looking like this. Okay, this is the surface.